In our previous lesson, we looked at how we could multiply polynomials. So we could multiply a monomial times a trinomial or a binomial, or multiply two binomials, or cube a binomial, or something along those lines. Now we're working in the opposite direction. So we're trying to break a polynomial into its factors. So the first type of factoring that we're going to look at is what I refer to as undistributing. We're basically looking to see, and this is really the first place you should always start with any kind of factoring, is to see if there's a common number or a common variable amongst all of the elements in the polynomial. So if we look at this first one, where we have 2x cubed minus 18x, hopefully we can see that we can divide a 2 out of, or factor out a 2 from each of those, and they also have at least an x in common. So we can undistribute that 2x. And now we have to figure out what's left behind inside the parentheses once we have factored out that 2x. And so in this case, 2x times what would get us back to 2x cubed? Well, we still have an x squared that's left behind. Minus, and then 2x times what equals 18x? Well, that's going to be a 9 here. And so that's, for now, as far as we're going to go. We'll see in a moment that we could factor this a little bit farther, but we'll just leave that here since we're just trying to focus on the undistributing. Now in the second example, it's a little bit more going on in terms of what we're going to be able to undistribute. It's a little bit subtle. It doesn't look like at first that there's any common single number or variable, but if we rethink of this, maybe think of x minus 5, let's replace it with like a giant A. So if instead of writing x minus 5 in parentheses squared plus 8 times x minus 5, what if we wrote it as a squared plus 8a? If I wrote it like that, hopefully we'd recognize that there's an a in common that we could undistribute from both pieces, and so then we'd be left with a plus 8. Well, that's essentially the approach that we're going to take here, except instead of a, we can factor out an entire set of parentheses, this x minus 5. That's what's in common in the two parts of this problem. Both parts, separated by the addition sign, have an x minus 5. So I'm going to factor out an x minus 5 from this expression. And so from the first part here, I've taken out one of the x minus 5s, but I still have one more left behind. So if I was to redistribute, x minus 5 times that x minus 5 would give me x minus 5 squared, plus, and now from the second part of the problem, I have removed the only x minus 5, but I still have an 8 left behind. And then just for simplifying purposes, I'm just going to clean up what's going on inside of this giant set of parentheses here, since the parentheses around that x minus 5 don't really mean much anymore. So I've got this initial x minus 5 that I factored out, and then x minus 5 plus 8 leaves me with x plus 3. So that's a fairly subtle thing that we have to pick up on in terms of seeing that we can undistribute from that type of expression. If that was a little bit difficult, you'll see a couple of those in the homework. I'll also make sure that we look at those in our future warm-ups as well. Now, before moving on to more examples, I first want to take a look at 3 kind of significant patterns that we have to pay attention to when they come up, sort of irregularities from most of our factoring, which is just kind of a reverse FOIL process. The first is the difference of squares. And so we kind of had an example of that already up here with this x squared minus 9. But hopefully we recall this idea that if we're subtracting 2 perfect squares, this is a circumstance where the first term that we're looking at and the second term in our polynomial, they are both perfect squares. So then we can factor into this x plus, or u plus v, u minus v pattern. So in the case of what we see here, hopefully we can recall that this would be like x squared minus 3 squared, and so it would factor into x plus 3 times x minus 3 if we were to finish that out. So hopefully that's familiar. The other two that are here are just patterns that we have to memorize as well. So that's for the sum of cubes and for the difference of two cubes. So now it's when we have a sum of two cubes, so like let's say it was x cubed plus 27. So x cubed is a perfect cube, 27 is a perfect cube. That factors into the pattern that we see here. So we have to identify what are kind of the cube roots of each of those pieces. So we've got the u, the v, and then the remaining part of the factorization follows the pattern that's there in the parentheses. And then we have a pattern for a difference of cubes as well. So we'll see those put into practice in some of our examples, so hopefully that will make those a little bit clearer. What you'll notice is missing here is a sum of squares. So let's say it was x squared plus 25. So x squared is a perfect square, 25 is a perfect square. So we might be thinking, all right, well, what does that factor into? Well, maybe x plus 5 times x plus 5. But if we try to refoil that, we're going to see that that does not remultiply into x squared plus 25. We're going to end up with an extra plus 10x in the middle. Maybe if we made them both minus instead of plus, same problem. We're going to get the x squared that we want, we're going to get the 25 that we want, but we're going to miss out on the correct answer because we're going to have a minus 10x in the middle. And then of course if we make one positive and one negative, then we're going to end up with x squared minus 25 if we remultiply that. So there is no way to factor a sum of squares. It is not factorable. This would be as simplified as it gets. So in the next video, we'll take a look at all of these types of factoring. The undistributing combined with just some regular reverse FOIL, as well as these patterns, difference of squares, sum of cubes, difference of cubes, and apply those to all sorts of examples.